We present MotionDiffuser, a learned representation for controllable multi-agent motion prediction using denoising diffusion models. Our model sequentially evolves a set of random samples into a diverse and multimodal joint distribution over future outcomes. MotionDiffuser learns a distribution over agent trajectories that is diverse, simple, requiring a single L2 loss, and permutation invariant over multiple agents. MotionDiffuser enables sampling under constraints, such as enforcing rules and physical priors, or creating tailored simulation scenarios. MotionDiffuser also enables computation of the exact log probabilities per trajectory. Finally, we achieve state-of-the-art results for multi-agent motion prediction. We briefly present an overview of the model architecture as follows. Scene inputs such as agent history, context agents, traffic lights, and road graph are first encoded using a powerful transformer-based scene encoder. This produces a set of learned latent tokens which represent the input scene. The core component of MotionDiffuser is a transformer-based denoiser that is permutation invariant with respect to the set of modeled agents. During training, a random normal noise vector is added to the set of ground truth trajectories. The denoiser receives the noisy trajectory and regresses the denoise trajectory using a simple L2 loss. This entire process can be trained end-to-end along with the encoder. During inference, we sample a set of random normal vectors to initialize the output trajectories. While the scene inputs are encoded only once, the denoiser repeatedly attends to the condition tokens and the noisy trajectories to iteratively denoise the predictions. This sampling process can be further biased by an optional constraint gradient to obtain a distribution of predictions that satisfy a certain set of constraints. The entire model is trained end-to-end using a single L2 loss objective. The denoiser takes in a noisy ground truth trajectory and regresses for the original ground truth trajectory. The score function, mathematically defined as the gradient of the estimated log probability, can be derived from the denoiser output. At sampling time, an initial set of random normal samples follow the score function to be denoised into the final set of predictions. Furthermore, we can perform constrained trajectory sampling by injecting additional constraints in the form of a differentiable cost function. The key insight is to sample from the joint conditional distribution between the learned distribution and the constraint distribution. The combined score function can be seen as a simple addition of the two scores. The constraint score can be approximated by the gradients with respect to the differentiable cost on the denoise trajectories. Using the diffusion modeling formulation, we can compute the exact log probability score for any trajectory sample. We visualize the corresponding log probability scores of the predicted trajectories on the right. While the model predicts a diverse set of possible future outcomes, less probable outcomes have lower associated probabilities. We represent agent trajectories as their corresponding top 10 PCA components. Contrary to other signal modalities such as images, trajectories are naturally smooth and continuous, and can be effectively compressed with very few PCA components. A mere 10 PCA components can reconstruct the original trajectory to within 6 centimeters of reconstruction error. Using the PCA representation leads to more efficient diffusion sampling, effective filtering of perception noise, better motion prediction performance, and makes it much easier to enforce sparse constraints at inference time. We report our performance on the interactive subset from the Waymo Open Motion dataset. We achieve state-of-the-art performance across many scene-level metrics, including minimum average displacement error, minimum final displacement error, and miss rate. We achieve very competitive performance across other metrics such as mean average precision and overlap. Compared to the waveformer model, which shares an identical encoder architecture, MotionDiffuser achieves significant improvement across all metrics by utilizing a diffusion predictor head and the denoising loss function. We further demonstrate our model's constrained sampling capabilities. We compare to a simple baseline that performs an optimization step to post-process predicted trajectories. The baseline is effective at enforcing constraints, but fails to produce realistic trajectories. Our model produces both well-constrained and realistic trajectory samples. We demonstrate quantitative assessments for the realism of trajectories, as well as the effectiveness of the constraints. Our constraint sampling is both effective at enforcing constraints and produces realistic trajectories. Finally, we perform an ablation study over several key design choices, including the use of PCA representation and the use of self-attention in our transformer-based denoiser architecture. Our combination of design choices produces the best overall results. Thank you for watching.